Hey guys, welcome to FactZ. Have you ever wondered if gravity might just be an imaginary concept that mathematicians invented for their convenience? Well, this might sound crazy, but it's a serious question. Think about it. Some of the biggest mysteries in science, black holes, quantum mechanics, string theory, all these unanswered questions could be because the concept of gravity itself might be flawed. Yep, I know that sounds wild, but give me 5 minutes and I'll explain everything. Let's start with something simple. Why is this bottle solid? Most of you would say, because of the fundamental forces, and you'd be right. Strong nuclear force, weak nuclear force, and electromagnetic force hold the atoms of this bottle together, keeping it solid. These forces work both at the atomic level and the larger macro level. But here's the thing, gravity, you can't even detect it at small levels like that. It only shows up when these forces combine atoms to form objects with mass, and that mass creates gravity. So is gravity really a fundamental force of nature? Does it even exist on its own? Here's where things get interesting. When we looked into this, we found something surprising. Even the gravitational constant isn't actually constant. It changes every 5.9 years. Crazy, right? So this begs the question, did physicists create gravity just to make the math easier? Let's dig deeper, because what we've been taught about gravity might not be entirely correct. You see, gravity is an abstract concept. We can perceive it, we can feel it, but we don't have solid, concrete evidence of its source. And whenever we deal with abstract ideas, something called confirmation bias kicks in. It's our natural tendency to find new evidence that supports what we already believe. Here's an example. If I throw a ball straight up, what do you think is the direction of the net force acting on it at different points? Going up, at the top, and coming down. Take a second, pause the video and comment your answer. Done? Alright, if you said the force is upwards while the ball is going up, downward at the top, or downward when coming back down, you're wrong. Many people make this mistake. The correct answer is that the force is downward in all three cases. This might seem counterintuitive at first. Why? Because once the ball is thrown, the only force acting on it is gravity, which always pulls downward. Gravity is a constant force that never changes direction. So why did so many people get this wrong? It's a common misconception. It's because of confirmation bias. Our brains are wired to make quick judgments. We're logically biased to think that motion and force should have the same direction. This is a natural assumption. But it's not just regular folks like us. Even scientists face these biases, and they have to work hard to overcome them. And this has made understanding gravity really tough. It's a challenging concept that requires careful thought and study. Take René Descartes, for instance. He had this idea called the vortex theory, where the entire planetary system was located in a transparent vortex, with the sun at the center and the planets swirling around it. This vortex, he thought, was why planets seem to be drawn towards the sun, just like boats get pulled toward the center of a whirlpool. He believed that force couldn't be transferred without a medium. But Descartes couldn't explain where this vortex actually came from. This is where Newton entered the scene, forever changing our understanding of the universe. Newton believed in fixed space, and Descartes' vortex didn't fit with his view. Newton's ideas were revolutionary, challenging the established norms of his time. Newton hit right at the weak point of Descartes' theory, the source of gravity. He questioned how objects could influence each other without direct contact. Newton needed to prove the existence of gravity between two objects that attract each other, and at the time, scientists were already discussing how Jupiter might be influencing Saturn's orbit. This was a perfect opportunity for Newton to test his ideas. Newton got curious and asked for data on Jupiter and Saturn's orbits. He meticulously analyzed the information, looking for patterns and anomalies. The data confirmed his suspicions. The mass of Jupiter was affecting Saturn's orbit. This was a groundbreaking discovery that provided the evidence he needed. From this, Newton concluded that any object with mass attracts other objects with mass through gravity, and that's how the universal law of gravitation was born. This law would go on to explain not just planetary motion, but the behavior of objects on Earth as well. But even Newton faced a problem. While he could describe gravity and its effects, he couldn't explain why mass creates attraction. In fact, Newton once wrote that although he knew gravity was an inherent property, he had no idea what caused it. This mystery remained unsolved for over 230 years, baffling scientists and thinkers alike. Until Albert Einstein came along in 1916 with his groundbreaking general theory of relativity. Einstein flipped the script on gravity, offering a revolutionary perspective. He demonstrated that the mass of any object warps the space-time fabric, creating gravitational effects that we observe. And he also predicted that if the sun were to suddenly disappear, its gravity would vanish too. But we wouldn't notice this change for 8 whole minutes due to the speed of light. To make this concept clearer, Einstein's theory sounds pretty solid and revolutionary, right? But here's the kicker. At the quantum level, general relativity completely falls apart. It can't even explain large objects like black holes properly. Back in the day, quantum mechanics was trying to explain the universe at a fundamental level and suggested that every force, matter, and energy had a fundamental particle. It correctly predicted particles for the electromagnetic force, photons' strong nuclear force, gluons and weak nuclear force, W and Z bosons. It even predicted that there should be a particle for gravity, called the graviton. But here's the thing. Despite decades of research and massive particle colliders like the Large Hadron Collider, no one has ever detected a graviton. Some scientists say detecting it would require colliding particles the size of Earth, and the detector would collapse under its own gravity. So, what is gravity? Well, nobody really knows. Some scientists believe we might be able to explain gravity by combining quantum mechanics and general relativity. But, spoiler alert, the answer is no. Quantum mechanics views space as made up of discrete chunks, while general relativity treats space as a continuous fabric. Plus, quantum mechanics relies on background information, while general relativity doesn't. Still, in my personal opinion, quantum mechanics could eventually crack the code on gravity, just like it did with simulation theory. By the way, if you want a video on simulation theory, drop a comment below, and don't forget to subscribe to FactZ. Stay curious, keep learning, and keep growing.